All right, let's talk about something that can be quietly costing your business a fortune. We're going to uncover a hidden problem, kind of an invisible thief, that's operating inside your electrical system, just wasting energy and driving up your bills.
So let's kick things off with a bit of a mystery. Maybe you've seen the signs. Your equipment's running way too hot, right? You're getting hit with these confusing penalties and, these demand charges on your utility bill. And you've just got this nagging feeling that you're paying for energy that just disappears. So what's the real story? What's behind all this wasted energy and money?
Well, the culprit, the name of this thief, is something called low power factor. Now, what is that? In the simplest terms, it's just a number. It's a measurement of how efficiently your equipment is actually using the electricity it's pulling. A low number? That's bad news. It means your system is super inefficient, drawing way more power from the grid than it's actually using to get real work done. Okay, to really get a handle on this, let's use a classic analogy that I think you'll appreciate: a simple glass of beer. Just imagine the whole mug represents the total power your utility has to provide. So first up, we've got what's called real power. This is measured in kilowatts, and it's the good stuff. It's the actual liquid beer in the glass. This is the power that does real useful work, lighting up a room, creating heat, or actually turning the shaft on a motor. Next, there's reactive power, and this is measured in kVAR. Just think of this as the foam on top of the beer. It takes up space in the mug, right? Space you're paying for, but it doesn't do any useful work itself. Now, it's not totally useless, I should say. It's absolutely essential for things like motors and transformers to create the magnetic fields they need to run. And last but not least, we have apparent power, measured in kVA. This is the whole shebang, the entire mug, beer, and foam combined. It represents the total amount of power your utility has to be prepared to deliver to you. And think about it. They have to build all their infrastructure, their cables, transformers, everything, big enough to handle that entire mug. So, here's the key takeaway, the most important part of this whole analogy. Power factor is just the ratio of the real power, the beer, to the apparent power, the whole mug. It's that simple. So a high power factor, something close to 1, means your mug is pretty much all beer, very little foam. Awesome. But a low power factor, that means your system has way too much foam and you're paying for a full mug, but getting a whole lot less useful work done. All right, section 2, why your power lags, the physics of the problem. So now we know what the problem is, but the big question is, why does it happen? Where does all this foam, this reactive power, actually come from? Well, the answer is something called inductive loads. And these things are absolutely everywhere in any industrial or commercial building. We're talking motors, transformers, industrial punks, even the ballasts in older fluorescent lights. All of these devices need reactive power just to build and maintain the magnetic fields that make them work. Okay, now this is where it gets really interesting, because you can actually see the difference. On the left, you've got a simple resistive load, like a basic electric heater. See how the voltage and current are perfectly in sync? They rise and fall together. But now, look at the right. With an inductive load, like a motor, the energy it takes to build up that magnetic field creates a sort of magnetic inertia. It actually delays the flow of current. The current wave falls behind, or lags, the voltage wave. And that lag, right there, is the root cause of a low power factor. Section 3, the true cost of waste, quantifying the damage. Okay, so this lag we just talked about, it's not just some nerdy technical detail. No way. It has serious, and I mean escalating, financial consequences. This is where the problem really starts to hurt. Just take a look at this chart. As your power factor drops, the energy you lose just as wasted heat in your own wiring doesn't just increase a little bit. It absolutely skyrockets. At a power factor of 0.8, which isn't even that terrible, your energy loss is already up by 156%. Let it drop to 0.7, it's over 200%. And at 0.6, it's a massive 278%. That is literally money just turning into heat for no reason. And this leads to what I call the double penalty. It's a brutal 1-2 punch. First, penalty number 1, you pay for the electricity that's being wasted as heat in your cables and transformers. But then, and here comes the second hit, if that equipment is in an air-conditioned space, you have to pay again to run your HVAC system just to get rid of that same heat. You're paying to create waste and then paying to clean it up. It's crazy.
And believe me, the damage doesn't stop there. On top of everything else, your utility is probably hitting you with direct penalties and those high demand charges. You're wasting precious capacity on your existing transformers, which might force you into an expensive upgrade you don't even need. That extra heat, it's slowly killing your equipment, shortening its lifespan. And the voltage drops it causes can trip sensitive systems, leading to really costly downtime.
Section 4. Fixing the factor. The hero arrives. So the big question is, how do we fight back? How do we stop this invisible thief? Well, it's time to introduce the hero of our story, the capacitor.
So, what does a capacitor do? Well, you can think of it like a local reservoir for reactive power. Instead of having to pull all that foam from the utility grid, which could be miles away, the capacitors supply it right there on site, exactly where it's needed. They create this opposite electrical effect, a leading current, that basically cancels out the lagging current from your motors. It just brings the whole system back into beautiful balance. So, how do you actually do this? The whole process is really pretty straightforward. Step 1, you analyze your current electrical load to figure out how bad the problem really is. Step 2, you set a target, which is usually going to be above 0.95 because that's what most utilities want to see. Step 3, you calculate exactly how much correction, how many kVAR you need. And finally, step 4, you have the right-sized capacitor banks installed by a professional. It's a very clear, well-established engineering solution.
Section 5. The efficiency payoff. The strategic benefits. Now, fixing your power factor is about so much more than just solving a technical problem or dodging a penalty. It's truly a smart, strategic investment in the efficiency and even the resilience of your entire operation.
And the payoff? Oh, it's immediate, and it is significant. For starters, you'll immediately eliminate those annoying penalty fees from your utility bill. Poof, they're gone. You'll also free up capacity on your existing equipment, which is huge. It could mean delaying a really expensive upgrade. You're going to reduce energy waste, which lowers your bills and your carbon footprint. And by cutting down on heat and stabilizing your voltage, you're actually extending the life of your most critical, expensive equipment.
And hey, you don't have to just take my word for it. This quote from National Grid says it all. A comparatively small improvement in power factor can bring about a significant reduction in losses. That's the key right there. Even a small fix can lead to massive savings. Honestly, it's one of the best return on investment projects you can do for your electrical system. So that kind of leaves us with one final thought to chew on. Now that you know how to spot this invisible thief, now that you know what to look for on your bill and what that sound of overheating equipment really means, it makes you wonder, right? What other hidden inefficiencies are lurking in your operations, just waiting to be discovered and turned into savings?